All right. Okay. Thank you for the kind invitation. So I will talk about representations and the emergence of space-time. Let me start by reminding you of what is a representation in mathematics. So traditional representation theory is about representations of Lie groups and Lie algebras, where we have a map into matrices that act on vector spaces. The point of a representation is that it is preserving the algebraic structure that it is representing. So for example, in the case of a Lie group, we have that whether we first multiply two elements of the Lie group and then represent that as a matrix, or we first represent both elements of the Lie group A and B as matrices and then multiply those matrices, that should be the same. And then we speak of a representation. Now more generally, we can view a representation to be any structure-preserving map. Oh, I see, I could also point to this here, right? Okay, so more generally, we can view a representation to be any structure-preserving map from some algebraic structure A into some other structure B. Examples are, for example, vector spaces. They're the abstract axioms of a vector space. That's an abstract thing. Any concrete vector space is a representation of it. In fact, in mathematics, there is a theory that is dedicated to structure-preserving maps, or representations, as we may also call them. And that theory is called category theory. And there they have objects that are called functors, and every functor can be interpreted as a structure-preserving map, so it's a representation in our sense. But I don't want this to be constrained to pure mathematics. For example, in quantum mechanics, we have abstract states and abstract operators, and they have representations, for example, position representations, momentum representations, and so on. In this particular case, they are equivalent by the Stone and von Neumann theorem. And then, more generally, there are approximate representations. An example is the classical phase space. We know that nature is actually described by quantum mechanics and its Poisson algebra. And yet we work with classical phase spaces when it comes to spacecraft engineering, for example, for flight path engineering, and many other circumstances in engineering where we still use classical phase spaces. So the classical phase space is an approximate representation of what is really going on, which is the quantum Poisson algebra. Also, for example, when an experimenter sets up a quantum circuit, what it is in the sense here is an approximate representation of an underlying quantum algorithm. For another example, we know that spacetime has curvature. We're not sure whether it has torsion. There is no evidence, no positive evidence that spacetime has torsion. But if one day super accurate measurements reveal that spacetime has torsion, then in hindsight we will realize that the way that we have been dealing with spacetime so far, namely torsionless and with curvature, was just an approximation to the real deal that was a spacetime that actually had curvature plus torsion. The point I want to make on that slide is that approximate representations can be really good. But in some regimes, these approximate representations can become bad approximations, or in some regimes, no such representation is even possible. For example, let's look at the first case, classical phase space approximating being an approximate representation of the quantum Poisson algebra. When it comes to the dynamics of electrons around a proton, then the classical phase space is really useless. It just doesn't work as a representation. It's not even an approximation anymore. Okay, so the point here is that approximate representations can have their regimes in which they're good, but in other regimes, the abstract structure just doesn't have this approximate representation. Now, let us talk about what we know for sure in physics, and they are quantum field theory and general relativity. And if we put the two together, we get quantum field theory on curved space-time. That's as far as we know physics for sure. So let's look at quantum field theory on curved space-time. Could it be that it is a representation of something more abstract? If that's the case, what could happen? What could happen, for example, at higher energy regimes that we have not explored yet? Well, what might happen is that at these higher energy regimes, this underlying structure, this underlying theory of which quantum field theory on curved space-time is a representation, it could be that at these higher energies, quantum field theory on curved space-time may no longer be a good representation. Or it may be useful as a representation, but maybe with a different dimension of space-time, or maybe something else changes. It could also be that at extreme scales, for example, the Planck scale, it could be that the theory, the abstract underlying theory, would be in a regime where it simply doesn't have a representation, even an approximate representation anymore in terms of quantum fields on a curved space-time. It would still be the same underlying theory. Just in one regime, it has this kind of representation, another regime, another kind of representation. And in some regime, it may not have any representation of the type that we know. So let's try that out. Let's search for an abstract, simpler structure of which quantum field theory in curved space-time is an approximate representation. And then when we have that underlying structure of which quantum field theory in curved space-time is an approximate representation, then let's see whether that underlying structure also has other representations in other regimes. Let's start with observation 1. There are two observations, and then we put them together. So observation 1 is that matter is completely describable through correlators. That's not news. If you've studied quantum field theory, you know that everything about it can be encoded or is encoded in the endpoint correlation functions of the quantum field theory. Now let me go off on a tangent for just a minute. We could now say, okay, that's cool. Everything about the dynamics of matter is encoded in endpoint correlation functions. That's information theoretic. And we could study now these correlation functions information theoretically. Quantum field theoretical interactions are classical and quantum channels. When one particle collides with another particle, then it transmits information automatically, classical information. There's a classical channel that's established when two elementary particles interact with each other. But also a quantum channel is established. If, for example, one of the collision partners was previously entangled with an ancilla, we can ask, where did this entanglement go? Which of the collision partners took away the entanglement? Or which one took more, which one took less of the entanglement away? These are questions of quantum channel capacity. And one of the things we are looking into in my group is to describe all of the interactions of quantum field theory of the standard model information theoretically only. Normally we think of interactions as being about the transfer of quantum numbers like momentum and energy and so on, but maybe the whole thing can be rephrased in terms of the classical and quantum channel capacities. And I think that's natural because the building blocks of this study are just the endpoint functions, they're correlators. And correlators are primarily information theoretic. But now let's move on to observation number 2. Observation number 2 is that not only matter is described by correlators, but also space-time is describable through correlators. And of course, many of you know that already. Namely that the metric can be expressed through the two-point correlation function in this way. You differentiate it, take it to some power, differentiate it, take the coincidence limit, certain prefactor, you get the metric. Why is this possible? Well, it's possible because the two-point correlator is, in the ultraviolet, a function that of the geodesic distance. And if you have geodesic distances, you can calculate the metric, because the metric just gives you infinitesimal geodesic distances. So this means that space-time, the space-time metric, can be reconstructed from the two-point function, or put it differently, a space-time is normally viewed as a differentiable manifold with a metric, but it can also be viewed as a differentiable manifold with a two-point function. So the summary so far is this. Putting together observations 1 and 2, we find that both matter and space-time are expressible through the quantum field theoretical endpoint functions. Now, is this the deep underlying theory that we were looking for here, of which quantum field theory and curved space-time is a representation? Hardly, because we just look at things differently, but it's not that we have removed the representation aspect of it. What we want is to see quantum field theory on curved space-time as a representation of something more abstract. What could that be? Now here we notice that these endpoint functions are functions of a bunch of variables. And these variables are space-time coordinates. This assumes that there is a space-time manifold to start with. Is there a more abstract coordinate-free formulation of these endpoint correlators? And there is, and it's not mathematically all that new. Remember that in quantum mechanics, a Green's function, and these are in quantum mechanics, these are just the two-point functions. In quantum mechanics, a Green's function can be written in any basis. I can write it in the position basis, momentum basis, or any other basis, or no basis. For example, if this is the Green's function for the time evolution, then the abstract thing underlying it is just the time evolution operator. And the time evolution operator is an object unto itself. If you choose to express it in the position basis, you get the Green's function, but you don't have to choose a basis. It's an abstract operator on the Hilbert space, an operator with two arguments. And now here too, in quantum field theory, the correlators are written in a position representation, but really I could change coordinates in any which way we want. I could even Fourier transform or do Hilbert transforms on it. It doesn't matter. It's an operator. It's just that it is no longer an operator that has only two arguments. It's an operator that has n arguments, but it's still living on a Hilbert space of fields, just like this one was on wave functions with the batteries failing here. So in quantum mechanics, it was the Green's function acts on wave functions. In quantum field theory, it acts on fields. But mathematically, we can take out the representation. We can look at the abstract object that's behind the Gn, and of which this is just a position representation. So let's look at this Gn, this abstract Gn, operators on a Hilbert space of fields, which take n arguments. Now that gives us a coordinate-free description, an abstract description of quantum field theory in curved space-time. Or does it? Does it really constitute an equivalent way of describing quantum field theory in curved space-time? In quantum mechanics, we know that the time evolution operator does the job. I can just choose the position basis and I get back my Green's function. But here, what basis do I choose to get back those endpoint functions? Can I just choose a position basis? Well, what is a position basis? We don't have position operators in quantum mechanics, so we don't have the ability to pick position basis on the basis of they are the bases in which the position operators are diagonalized. We'll have to think of something else. So if the abstract Gn are supposed to be an equivalent description of quantum field theory in curved space-time, equivalent to actually writing them down as functions of position coordinates on a manifold, then we need to be able to get back to from the abstract Gn to the Gn of x1, x2, x3, etc. As I said, in quantum mechanics, it would be easy to get from the time evolution operator the Green's function in position space. I just diagonalize the position operators, and then I obtain a position basis, and I can write my time evolution operator as a Green's function, and everything is as it was. Here, we can adopt a similar strategy even in the absence of position operators. Namely, what we can do is, first fix this typo here. So what we can do is we can use the locality of interactions in quantum field theory to recover the position bases. Namely, the Gn for n larger than 2 describe interactions, and they are local. So instead of diagonalizing position operators in quantum mechanics, in quantum field theory, what we can do if we start in a basis-independent framework is that we can diagonalize the vertices. We can diagonalize the interaction terms, which we know is possible because interactions are local. So the coordinate bases, the position bases, are identified as those bases in which these endpoint functions are diagonal. We're relying here on the locality of the vertices, which is not a mathematical necessity, it's a physical necessity. So if the theory's interactions are indeed local, then the vertices for n larger than 2 are diagonalizable. Diagonalizing them, we obtain the bases in which those higher point functions are diagonal. And in particular, these are position bases, so we can write down these endpoint functions as functions of positions on a manifold again. Now, we use the vertices to determine the position representations, and that the vertices are for n larger than 2. But once we have the position representation, we can then also apply that to write down G2 with 2 arguments in the position basis. So that's this one. And that's great because from it we can recover the metric. So this means that indeed having just the abstract objects means we have all the information that was previously in the concrete Green's functions, because we can go back and forth between the abstract and the concrete. It also means, by the way, that you can hear the shape of a drum. You just have to drum it harder. Because if you drum a drum really hard, then it gets into the nonlinear regime. And the description of that is, if you describe the solution of that differential equation, nonlinear differential equation, what you do is you write down Feynman graphs. I mean, effectively, that's what you do when you solve for a nonlinear drum. And what we just showed is that if you have the vertices, you can actually get from the spectrum of the second derivative, from the 2-point function, you can get the metric. Now, the drum, of course, is a flat case spectral geometry. It's more interesting when it's about the shape of a vase or shape of an object, but the same argument applies. So as long as you get into the nonlinear regime, you can recover the shape from the sound. Okay, so now we have an abstract description of quantum field theories on curved space-time. But given let's say you start with these. You give yourself some operators, G superscript n, where n indicates how many arguments this operator takes in. You just pick arbitrary ones. Can they be represented as in terms of a quantum field theory that lives on a curved space-time? In general, of course not. And that's because the endpoint functions for n larger than 2, so the vertices, the interactions, they have no mathematical reason to be diagonalizable. So in general, no, the abstract structure doesn't have a representation in terms of quantum fields that live on a curved space-time. We know from physics that in some energy regimes, the actual Gn do have at least an approximate representation, which is, we know that the vertices of quantum field theory are diagonalizable, at least to the extent that we can measure locality, at least down to about 10 to the minus 21 meters, which is what the LHC can resolve. So we know from experience, from experiment ultimately, that the actual Gn that rule what we know they are approximately diagonalizable in the low energy regime. But we also know that in general, generic Gn have no reason to be truly, fully diagonalizable. Which means that in general, if you just pick some random Gn operators on some Hilbert space, then they do not possess a representation as quantum field theoretical correlators on a space-time. At best at low energies, but in general, no reason that they would. So the summary so far is that space-time and matter are describable by a collection of abstract n-point correlators, which are just operators on a Hilbert space with n arguments. And a priori, the set of all representations of the Gn that we obtain from the physics as we know it. So if we take the standard model and we lift it to this abstract description that doesn't rely on a position representation anymore, then this abstract structure may also have other representations other than the ones we usually use. For example, quantum reference frames might be just other representations of the same abstract structure. Who knows, maybe even dualities such as ADS-CFT are just instances of an abstract structure having two representations. So this is about the Gn that we lift from the standard model of physics. However, generic Gn, if we just pull some out of the hat, if we just make up some Gns, then they're at best approximately representable as quantum field theoretical correlators on a curved space-time, at best at low energies. In general, there's no reason to expect that they really are diagonalizable, the vertices, the higher point functions, the interactions, and therefore we do not have an exact representation in terms of quantum field theoretical correlators on a curved space-time. So in this way, quantum field theory could be an approximate representation of a more general theory that we might call pre-geometric, because it doesn't assume that there's a manifold underlying, but it allows it to happen in regimes where the vertices are diagonalizable. So what could be a theory of these abstract Gns? I won't say much about it here, because I want to give an explicit example later, but abstractly what we can say is this. The Gns are the Taylor coefficients of the partition function. So all of them together can be handled at once by just looking at the partition function. The partition function, on the other hand, is the Fourier transform of e to the power is. If you didn't know that before, let me tell you, to solve a quantum problem is to do a Fourier transform. To solve a classical problem is to do a Legendre transform. What we see here is that to solve a quantum problem is to obtain the partition function. And how do you do it? You Fourier transform this. This is the function to be Fourier transformed, S of phi. And here we have the Fourier factor, e to the power of I times j phi. This is the old variable. This is the new variable of the Fourier transform. It's just continuously infinitely many Fourier transforms all at once. The point is, Fourier transforms are invertible. And yes, you can calculate from the classical action what the partition function is, but you can also do the Fourier transform of the partition function. That's another path integral, and you get the classical action back. It's one-to-one. And a priori, there's no reason we should get hung up on the classical action. Yes, we've started with classical actions for more than 100 years. But this is where the music plays, right? This is what we really want, the endpoint functions, the coefficients, the Taylor coefficients of the partition function. And those are described information theoretically. Why not do the information theory of that? You see, a one-point function, that's a probability distribution. This is all about von Neumann entropies, Rényi entropies, and so on. Two-point functions, we have tools for that. Mutual information, coherent information, classical and quantum channel capacities, negativity, and so on. And then for 3 and 4 and higher point functions, we get the whole higher order web of informational relationships. So I'm advocating to study this rather than that. And then once we've fully understood this, we can always do a Fourier transform and reinterpret what we have in terms of that. Anyway, recently with the two postdocs, Markus Reitz and Barbara Schroeder, we got a paper in PRL accepted. Here is it, and it's not yet out, but should be very soon. Here's the archive number. And we did an explicit example of all of this. For that, we started, and I'm just summarizing the paper because I'm running out of time, I'm summarizing the paper. We start with the theory of a number of free bosons, a number NF of free fermions, and gravity. So in principle, the bosons and the fermions are free, but they interact via gravity, and only via gravity. We did that for simplicity, not to make it realistic. It would be much more realistic to put interactions in there. But in this way, assuming the particles interact only through gravity, we were able to calculate the partition function explicitly. So we start with the theory of free bosons, free fermions, and gravity on a space-time as usual. And then we express that theory in a coordinate and therefore basis-independent way. Just lift everything so it's completely abstract. And once we have that abstract theory, we can then, of course, recover what we started with, namely that theory of N bosons and F fermions on a space-time with curvature. But having the abstract theory, we can now search for regimes in which no such representation exists, or maybe a representation in terms of quantum fields in curved space-time, but at another space-time dimension. So we calculated the partition function of that, and then we calculated the space-time dimension. So whenever the abstract theory has a space-time representation, whenever the abstract theory has a representation in terms of quantum fields that live on a curved space-time, we ask, well, what dimension does it have? And let me remind you that Hermann Weyl, 100 years ago, already figured out that if you know the spectrum of a wave operator, then the density of the eigenvalues of the wave operator is indicative of the dimension of the manifold on which the wave operator lives. And it's this little d, that's the dimension of the manifold. So it's a particular scaling. It's quite plausible. Think of a particle in a box. One particle in a one-dimensional box has a spectral, the spectrum is n squared, for n being the integers. But if it's in a two-dimensional box, then it's n1 squared plus n2 squared. If it's in a three-dimensional box, it's n1 squared plus n2 squared and 3 plus n3 squared. And the spacing of these eigenvalues is different, and it's indicative of the dimension in which this happens. So Weyl already discovered that, and it applies for curved space too, as long as the curvature radius is smaller, is larger than the scale of the wavelengths that we are dealing with, of the wavelength of the waves that correspond to the eigenvalues in question. So what we did is we took the abstract theory, we calculated the probability distribution for the spectrum of the wave operator, and then, or wave operators, and what we found is that using Weyl scaling, the dimension, when it exists, whenever the theory has a regime in which it can be represented in terms of quantum field theory on curved space-time, the space-time has to have this dimension. It's 2 plus the number of fermion species minus n times, 2 plus the number of fermion species minus the number of boson species. Which means that it is as if there is a Fermi pressure. You see, the larger NF there's a Fermi pressure to expand the dimension of the spacetime. Not just the dimension, not just the size of the spacetime itself. We calculated that too. But also, there's a Fermi pressure to expand, to enlarge the dimension of the spacetime. And then there is a bosonic pull to reduce the dimension of the spacetime. Thank you. Right. And so what that means is, okay, so we obtain that dimension, that the dimension depends on the number of bosonic and fermionic species. But the number of bosonic and fermionic species, the effective number depends on the energy scale that we are looking at it. At low energies, you don't see all of the fermions and the bosons. At high energies, you activate them too, those that are having higher rest masses. So how many species you actually deal with depends on the energy scale that you look at it. And that means that this formula changes as you go up the energy scale, so the dimension can change. And here's an example. We start with 32 low mass fermions and 30 low mass bosons. And we get, in this case, that the effective space-time dimension is 4, so we have an approximate representation on the 4-dimensional space-time. And then we add And then we say, okay, but maybe there's one fermion species that's really massive at like medium masses, and 3 boson species at those medium masses, and that changes the balance of fermionic push and bosonic pull, and then the dimension drops to 2. Of course, there are some regimes where we don't have a representation, right? It's like space-time boils up and then condenses again into 3 dimensions and then into 2 dimensions. Then in principle, you could imagine that as you go to higher and higher energies, the dimension might drop into the negative, so there is no representation in terms of quantum field theory on curved space-time anymore. It might also get stuck somewhere else, like in the transition regime here, so that there's no representation. In this way, space-time might emerge from a Planck scale. At the Planck scale, it just may not have the abstract structure may not have a representation in terms of quantum field theory on curved space-time, but then at lower energies, that representability is restored. And it might go through dimension changes as well. So what we found is, in the example, that space-time dimension depends on the bosonic pull versus the fermionic pressure. And this balance depends on the energy scale. And therefore, in some regimes, for example, the Planck regime, no positive integer dimension might come out, and therefore no space-time representation. It would be impossible to represent that abstract structure on as a quantum field theory on a curved space-time. Then you let the energy drop, and then the same abstract structure becomes representable, let's say on 2 dimensions, and then at even lower energies, it becomes representable in 4 dimensions. The overall message of my talk then is this. The physics of the emergence of space, time, and matter could be, mathematically speaking, the emergence of the representability of an underlying abstract, presumably information theoretic structure, as quantum fields on a space-time manifold. And maybe Carl Sagan anticipated it all when he said very wisely that the cosmos is within us. We're made of star stuff. We are a way for the universe to know itself. Thank you.